Welcome everyone to this lecture, A First Look at a Neural Network. In this notebook, we're going to take an introductory overview of neural networks, covering fundamental concepts and basic implementation. So, what exactly is a neural network? A neural network is a computational model inspired by the structure and function of biological neural networks. Think of it like trying to replicate how our own brains process information. It's designed to recognize patterns and make decisions by processing data through layers of interconnected nodes, which we call neurons. First off, they are inspired by the brain. They really do mimic the way neurons in the human brain process information. They are great at pattern recognition. They are particularly good at identifying complex patterns in data that are difficult for traditional algorithms to find. And importantly, they have the ability to neural networks learn from data by adjusting the connections or weights between neurons. Now, let's look at the basic structure. A simple neural network typically consists of three types of layers. The input layer. This is where the network receives the initial data. Each neuron in this layer represents a feature of the input data. Then we have the hidden layers. These are the intermediate layers where the network performs computations and extracts features from the input data. You can have one or even many hidden layers. Finally, the output layer. This layer produces the final result or prediction. The number of neurons here depends on the task you're trying to solve. For instance, one neuron for binary classification or multiple for multi-class classification or regression problems. Let's just visualize a simple neural network structure conceptually. This is just a diagram to help us understand, not actual code to build a network. Imagine our input layer has two neurons, say representing two features. Then imagine a hidden layer with three neurons. And finally, imagine an output layer with one neuron, for example, for binary classification. The key here is that connections exist between neurons in adjacent layers, and these connections have weights that are learned during the training process. Now let's dive a little deeper into how it works, the neuron. Each individual neuron in a neural network performs a pretty simple computation. First, it does a weighted sum. It receives inputs from the previous layer, multiplies each input by a corresponding weight, and then sums these weighted inputs. The formula for this weighted sum, which we often denote as Z, is this. After the weighted sum, the result is passed through an activation function. This is really important because it introduces nonlinearity into the network. Without it, the network could only learn linear relationships. Common activation functions you'll encounter include the sigmoid function, defined by this formula. ReLU, which stands for rectified linear unit, is given by this formula. And the tan H, or hyperbolic tangent, which is given by this formula. The output of this activation function is what becomes the input to the neurons in the next layer. We often denote the output of the neuron as A, and it's simply the activation function F applied to the weighted sum Z's. Let's see these activation functions in action by defining them in code and plotting them. We'll use the NumPy library for numerical calculations and Matplotlib for plotting. We define functions for sigmoid, ReLU, and tan H. We generate some input values and then plot each of these functions so you can see their characteristic shapes. You can see how sigmoid squashes values between 0 and 1, ReLU is 0 for negative inputs and linear for positive, and tan H squashes values between -1 and 1. Next, let's talk about the learning process, training the network. Neural networks learn by adjusting their weights and biases. They do this based on how different their predictions are from the actual correct values. This difference is what we call the error. This learning process is called training, and typically involves these steps. It starts with the forward pass. Input data is fed through the network, moving layer by layer until it produces an output prediction. And then we calculate loss. We use a loss function to measure the discrepancy between the network's prediction and the true target value. Some common loss functions are mean squared error, or MSE, which is often used for regression tasks. The formula is this, and cross entropy loss, commonly used for classification. The formula of this: after calculating the loss, we go through the backward pass, also known as backpropagation. The error is propagated backward through the network. During this process, we calculate the gradients of the loss function with respect to the weights and biases. Finally, the weight update, we use an optimization algorithm like gradient descent to use these gradients to adjust the weights and biases. The goal is to adjust them in a way that reduces the loss. The formula for the new weight is this. Alpha is the learning rate, which controls how big of a step we take when updating the weight. This whole process, forward pass, loss calculation, backward pass, and weight update, is repeated many times for many epochs until the network's performance on the training data is satisfactory. Here's a simple conceptual example of a loss function, mean squared error. We define a Python function that takes the true values and the predicted values and calculates the mean squared error. We then use some example true and predicted arrays to demonstrate how to use the function and print the resulting mean squared error. Now, let's look at a simple implementation example using Keras and TensorFlow. We're going to create a very basic neural network to demonstrate the fundamental structure and training process using a popular deep learning library called Keras, which is part of TensorFlow. Just a note, you'll need to have TensorFlow installed for this. We import the necessary libraries, TensorFlow and Keras. If the import is successful, we print a confirmation message. All right, let's build and train a simple model for a basic regression task. We'll generate some artificial data for this example. We generate random training data for our input xtrain and then create corresponding output values ytrain using a simple linear relationship with some added random noise. We build a simple sequential model. It has one hidden layer with 10 neurons and uses the ReLU activation function, and an output layer with just one neuron since it's a regression task. We compile the model, specifying the atom optimizer and using mean squared error as the loss function. Then we train the model using our generated training data for 50 epochs. After training is complete, we make a prediction with a new input value, 5.0, and print the predicted output. Finally, we plot the training loss over the epochs. The output shows the prediction the model made for the input 5.0, and you can see the plot illustrating how the model's training loss decreased over the 50 epochs. In conclusion, this notebook has given us a basic introduction to neural networks. We've covered their structure, how individual neurons work, and the fundamental process of training a network. Keep in mind, this is just scratching the surface. Neural networks are a vast and quickly evolving field with many different architectures and applications.